Hi, I'm Ms. Hearn. Let's get started. In this video, we're going to talk about several numeration systems. We're going to talk about the features of positional numeration systems, understand Hindu-Arabic numeration, understand Babylonian numeration, Mayan numeration, and Greek numeration. We're actually pretty familiar with Hindu-Arabic numeration since it's our own number system. And the digits convey two things. They convey a face value and a place value. Place values in our number system are all powers of 10, so we call it the base 10 number system. In this particular number, the 4s, of which we have 3, are in different positions, so they have the same face value, 4, but different place values. The 4 furthest to the right is just the number 4 because it's in the units position. The 4 that's in the middle is the hundreds place, so that represents the number 400. And the 4 that's furthest to the left is in the 10,000ths place, so that represents the number 40,000. This type of number system is called positional numeration. In a positional numeral, each symbol, called a digit, conveys two things: a face value, which is the inherent value of the symbol, and the place value, the power of the base, which is associated with the position that the digit occupies in the numeral. The important thing about a positional system is it's an improvement over some of the other historical systems that relied on multipliers. A positional system is one where the various powers of the base require no separate symbols. The power associated with each multiplier can be understood just based on the position that the multiplier occupies in the numeral. By contrast, let's recall what we learned about the Chinese system. The Chinese system would represent the number 7,482 historically, as it is shown on the right side over here. You would need a symbol for 7, the multiplier, and then a symbol for 1,000 to indicate the place value that we would observe in our number system simply by the position of the number 7. You'd need a 4 and a 100 to indicate 400. You would need an 8 and a 10 to indicate 80, and you would need the 2. If the Chinese system had evolved into a positional numbering system, it would look more like the number on the left, and it would be much more efficient. Let's look at another number system besides the Hindu-Arabic system that is positional. The ancient Babylonians used a modified base 60 number system. So what that means is that the digits in their system represented 1's place, 60's place, and then if you multiply 60 times 60, you get 3,600's place, and you could continue multiplying by 60 for larger place values. Interestingly, though, the Babylonians didn't have a different symbol for each of the numbers between 1 and 59, like we do for the numbers from 1 to 9. Instead, they just had two symbols, the inverted triangle for 1 and the wedge for 10, and they used those two symbols to construct all of the numbers from 1 up to 59. For example, the number 2 would be 2 inverted triangles, and the number 3 would be 3 inverted triangles. And sometimes they wrote them straight across like this, and other times they grouped them into two rows, one on top of the other, just to save space. So here, this might be one way to write a 4, and so on. If you wanted to write the number 11, you would need to have a 10, and then you would need to have a 1, so that would be 11. If you wanted to write 23, you would need the 3 1s, and you would need 2 of the 10s. That would be 23. Let's go ahead and convert these numbers from Babylonian numerals to Hindu-Arabic form, our regular number system. Let's start with A, and remember that the inverted triangle is 1 and the little wedge is a 10. So in A, we only have one grouping of 10s and 1s. This would mean that this entire thing would be a single digit to the Babylonians. So they're all in the 1s place. As opposed to in part B, where we have a grouping of 10s and 1s and then another grouping to the left of it, in which case they have a bigger place value, but we'll get to that in a minute. In part A, we're only looking at the 1s place. We have 3 10s and we have 4 1s. So we have 30 plus 4, or 34. Moving on to part B, as I already mentioned, we have 2 groupings of 10s and 1s. So this would indicate to the Babylonians that we have 2 place values. We have the 1's place value that has 3 10s and 5 1s. So that would be a 30 and a 5 for a total of 35. And these 35 are just worth 1 each. But then there's also these 2 1s in a separate grouping. Since it's in the second grouping to the left, that means that each of those 1s has a value of 60. So the 2 1s would normally be worth 2, but because of their position, it's 2 times 60, or 120. In our number system, this would be 120 plus 35 equals 155. Let's look at part C. Part C has more than one grouping as well. Again, we're looking at groupings of 10s and 1s. 10s and 1s, and then a little leftover over here. So we actually have 3 place values for this Babylonian number. In yellow, we have the 1's place. In green, we have the 60's place. The blue would then be the 3600's place. So let's figure out what digits we have starting with the 1's place. Here we have 3 10s and 5 1s, which is 35. And each of these 35 is only worth 1 because it's in the 1's place, so it truly is just 35. But when we look at the 60's place, where we have 2 10s and we have 1 single 1, this is going to be 21, but each of those 21 is actually worth 60. So that is actually going to be 1260. And then lastly, in the 3600's place, we have just 1 single 1, which would be worth 1, except that each one individual unit in this position is going to have a place value of 3600. So 1 times 3600 is 3600. And you have to add all these values together to get the total value of this number, 4,895. Okay, now let's go back the other way. Given a HinduArabic numeral, we're going to convert it to Babylonian. You have to kind of work backwards, starting with the largest place value that is less than the number you're given. So for example, in part A, we have the number 253. We can't have any of the 3600's place because that would just be too big. But we can have 60's. 60 goes into 253 several times. Now, one way to do this is using long division. So you write 60 next to 253. 60 can go into 253 about 4 times because 4 times 6 is 24. So 4 times 60 would be 240. You subtract, you get 13 as the remainder. 4 copies of 60 go into 253. That means that we need 4 of the 60's, which we can represent with 4 inverted triangles. I'm not going to color them in just to save time. And then, but we have 13 left over, so those 4 represent 240. It's not quite big enough. Well, we need 13 1's, and that can be represented with 3 1's for 3 and then a 10. So our number in Babylonian is going to look like this. All right, now we're going to look at writing 7,872 in the Babylonian number system. We need to think about what place values we might need to use. We definitely need a 1's place. 60 can go into 7872. So can 3600. So I actually need to check what's the next larger place value. 3600 times 60. Well, it turns out to be 216,000. Well, we don't have a number that big. So we're going to use a combination of multiples of 3600, 60, and 1 to come up with our 7,872. And the way that you do that is to use long division, starting with the largest place value you're going to use. So we're going to divide 3600 into 7,872. We can see how many of those 3600s we need. 36 goes into 78 twice. So I'm thinking this 3600 goes in twice. So 2 times 3600 is 7,200. We multiply, we subtract, and that leaves us with 672. And we would bring down, but there's nothing left to bring down. So this is actually the remainder here, 672. So you use the 2 to know how many 3600s you need, and you write 2 using 2 inverted triangles. The remainder is 672, and what we need to do with that is figure out how many 60s it takes to get close to 672, as close as we can. So now we're going to divide 60 into 672. 60 goes into 67 once. You multiply, subtract, bring down. So we're going to have 1 times 60 is 60. Subtract is 7. Bring down the 2. 60 goes into 72 once. 1 times 60 is 60. Subtract. And we have 12 left over as the remainder. So I'm going to write down 11. That's how many 60s we need. To write 11, we need a 10 and a 1. And then our remainder is 12. But the 12 is what we need to get from the ones place. So that just requires 12 ones, which looks like a 10 and 2 ones. So this is what the Babylonian number for 7,872 would look like. Now let's try 3,661. It's as large as 3,600 and not as large as the next place value. So how many times does 3,600 go into 3,661? Well, it only goes in once, right? And it actually leaves a remainder of 61. So we have 1, and we're going to put this symbol here for 1, and the remainder 61 we now need to divide by 60. So 60 goes into 61 once with a remainder of 1. So that means that we have a 1 here. We need a symbol for 1 in that position as well. And then we have a remainder of 1. So that's going to be written with a 1. So we need 1, 1 here as well. So this is an interesting number here. It would be very confusing in the Babylonian system to write the number 3,661. A person could very easily mistake it for just the number 3. What they would do is they would put extra space in between, but it still could cause problems. Another problem with the Babylonian system is that there is no digit 0. And so positional numeration systems really need a symbol for 0 to act as a placeholder in case one or more powers of the base are not needed. Suppose that in the Babylonian system we wanted to write the number 3,601. Well, 3,600, 60, and 1 are the place values, and we would need 1 3,600 and 1 digit 1, but we would need no 60s. So in fact, that number would look like 1 inverted triangle, nothing, and then another inverted triangle, which could easily be mistaken for 61 or even just the number 2. So the fact that it didn't have a 0 in it was a real problem for this number system. Now let's talk about the Mayan numeration system, a modified base 20 number system, which would normally mean if you have base 20 that you would have the value 1, the ones place, then you'd have the 20s place, multiply that by 20, you get the 400s place, and so on. But the Mayans actually, instead of a 400s place, used the 360s as their third place value. They multiplied by 18 instead of 20 just in that one instance. Then they continued to multiply by 20. So their place values look like this: 1, 20, 360, 360 times 20, which is 7,200, 7,200 times 20, which is 144,000. And the Mayan numerals were written from top to bottom, and the symbols that they used included 1 for 0. So this is a little bit more advanced. And here are the numbers from 0 to 19, so that you can see how they were used. So we have 0 is the symbol for 0, 1 is a single dot, 2 is 2 dots, 3 is 3 dots, 4 is 4 dots. And then they throw in a 5, a symbol for 5. that dash, and then 6 would be the dot on top of the dash, and you continue with that pattern to 9. 10 would be 2 dashes, and so on. Now, when we stack those digits on top of each other, we get the place values. You can tell looking at this that we're going to use 3 of the place values because we have 3 of the digits from the previous slide. So the top is going to be the 360s place. The second down is going to be the 20s place. And then we have the ones place. All right, so the way that we would figure out what this number actually represents in Hindu-Arabic form is just to multiply the face value times the place value. So let's start with the first position at the top there, the 360s place. That double dash, it's 2 5s. So 10 times 360, and then in the next place down, that's a 0. So that represents 0 times 20. And then in the third position down, that is the number 19, because 3 5s is 15 plus 4 dots is 19. But that's in the ones place, 19 times 1. So we're going to have 3600 plus 0 plus 19, which is 3619. Converting from Mayan to Hindu-Arabic is just a matter of multiplying the face value times the place value. Going back the other way involves division then, because we're reversing the process. So keeping in mind these symbols for 0 through 19, we're going to convert each Hindu-Arabic number to Mayan form. And we're going to use the same type of procedure that we did when we were converting Hindu-Arabic to Babylonian. It's just that the place values are different this time. 1s, 20s, 360s, and 7200s are the first 4 place values. For 49, you want to start with the largest place value that will go into 49. We can't use 360s or 7200s. 20 is the biggest that can go into 49. So 20 goes into 49 how many times? It goes in twice. Let's see how many are left over. So 2 times 20 is 40. Subtracting, we get a remainder of 9. I'm needing 2 20s. So I'm going to use the digit 2, and then my remainder was 9. So out of the ones place, I have to build the 9. So I'm going to use the digit 9. Okay, but in Mayan, we stack them biggest down to at the top, down to smallest at the bottom. So we're going to have the digit for 2, and then we're going to have the digit for 9. So this would be the number 49. Let's try 4,407. Okay, so for 4,407, we definitely cannot divide by 7,200. 360 is the biggest number out of the 3 place values that are left that can divide into that number. So let's do the long division. 360 goes into 4407. Okay, so 360 can actually go into 440 one time. So let's multiply 1 times 360. That gives us 360. After we multiply, we subtract. Subtracting 440 minus 360 gives us 80. Then we bring down, that's 7. Now we divide again. 360 goes into 807. How many times? Looks like twice, probably. 2 times 360 is 720. Yeah, that will work. So subtracting, we're going to get 87 as our remainder. So the number of groups of 360 that we need is 12 of them. 12 in Mayan looks like 2 5s and 2 1s. And then the remainder is 87. This 87 we have to construct out of the 20s and the 1s. So let's see how many 20s go into 87. 20 goes into 87 4 times. 4 times 20 is 80. We subtract and our remainder is 7. So we're going to need 4 groupings of 20. The 4 is just 4 dots and the remainder is 7. We need to build the 7 out of the 1s. So from the 1s, we're going to have 7 of them, which is represented with a 5 with 2 dots. Okay, so starting with the biggest place value, we build our number. So we have the top will be the 12 360s. The next digit would be the 4 20s. And then the next digit is going to be 7. That's the Mayan number for 4,407. Now the last numeration system we're going to talk about in this video is Greek numeration. The classical Greeks used a ciphered system. This means it had a lot of symbols. They actually had 27 individual symbols for numbers based on the 24 letters of the Greek alphabet, with 3 Phoenician letters thrown in there. So they have all the digits 1 through 9. So those are their ones place. And then in the tens place, they have a symbol for 10, a symbol for 20. All the multiples of 10 have their own symbol. And then in the hundreds place, all the multiples of 100 have their own symbol. So if we want to convert a Greek numeral to Hindu Arabic, translate or decipher like a little code. Alpha corresponds to 1, and the Greek letter mu here corresponds to 40. So you add them together, and that's just the number 41. The next one, we're going to look for theta. You're always going to get the ones digit from over here. So theta is actually the number 9. And then the tens digit is going to be one of these guys here. So pi is actually the number 80. And then chi, I think it's pronounced, is going to come from the hundreds place. So that looks like it's the number 600. So if you add those together, you get the number 689. All right, so that's our video on Mayan, Babylonian, Greek, and a little bit on our Hindu-Arabic number system. I hope you found this video helpful. If you did, please remember to give it a thumbs up. That helps other students to find the video.